Good morning. The purpose of this video is to help you through this um, assignment that's designed to replace our one-to-one time during class, and also to help you understand or develop some more fluency with some electrical concepts, which are really important for this segment this semester. So I'm just going to share my screen and take a look at the document that's got the assignment. The assignment has been sent to you as a PDF, but if you click on the link that's the title, it'll take you to a Google Doc. So whatever works for you. But I would like you to make a copy of this and then change the name to reflect your identity and the assignment. Like for instance, if I was doing it, it would be Chase Kitchen Circuit. So I'm going to ask you to design a household circuit, particularly the kitchen. There are different rooms in your apartment or your home that have different power requirements. The kitchen is one of the ones where there's more power required. So here are the elements that I would like to see in your design, and I've done an example for you. So I'm going to walk through that example. And there's a description about protection. Why does our apartment or our home need so many circuits? And the reason for it is you can actually see this is our circuit panel, and you take the cover of the panel off, and you can see the individual wires that actually run through the walls of the house. And they're actually not that thick. There are a couple of reasons for that. So thicker wires are more difficult to manipulate. They're also more expensive. So copper is a metal, and metals are can be very costly. So if we had thicker wires, we could run more current. But um, you know, it's relatively easy to have individual control, and that's kind of nice too. So the goal in this is to break up the power requirements in any kind of unit, whether it's an apartment, a home, or a manufacturing site. And when we spread out the power like this, we reduce the overall amount of current that's going through the wires. And that, number one, makes them more efficient. And number two, it reduces the load so it doesn't approach the maximum current that's capable of being passed through these wires without causing excessive heating. That heating, again, was going to reduce efficiency, but also poses a danger in starting fires. At any rate, let's go ahead and take a look at a circuit that I'm starting to use. So I provide you a link to a list of power ratings for household appliances, and you can find that at this link right here. And so I chose 5 different appliances, and feel free to duplicate at least 2 of them, but there are 3 that I would like you to pick independently. So this is a parallel circuit in your home. 120 volts is what our US standard is. And the reason why all the devices get 120 volts is because they're all wired in parallel. And that's a great standard because manufacturers can count on the fact that their devices are going to get charges that are delivering 120 units of energy per charge. But then the amount of current that gets used depends on the device, as you'll see. If we go over and take a look at the power outputs, I've got a couple of 1,000 watt um, items here, and then a couple of very low power items. So LEDs are replacing incandescent bulbs and hopefully replacing compact fluorescents. Compact fluorescents are more efficient than incandescent bulbs, but they also at the expense of introducing mercury into our environment if they're not handled properly. All right, so you can see I've already done the work here. The power values I've gotten from this lookup chart, and then the voltage is the same for all of them. So using these 2 relationships, if I divide power by voltage, I get current, and that's where I obtain these numbers. And then resistance is voltage divided by current, and then that's where the resistance values are. Now you can see that devices that use low power have a high resistance, and they don't draw very much current. A device like the microwave at 1,000 watts, and this is actually a small microwave, some of them are more like 1,500 watts. Has a low resistance, but it's not on very much. So it's only on usually for a minute or two. And so all in all, it doesn't really add up to your electrical bill very much. And so let's take a look at my coffee machine. So that's also 1,000 watts. So if I go and take the power 1,000 and divide by 120, then I'm going to get 8.33 for the current. And then if I divide 120 by 8.33, I'll get the resistance. And so that's 14.4. Again, low resistance because it's a high consumer. Now, let's turn our attention to the source. I made that in green because this is a little bit different. Everything that the devices that are listed under appliances, they're all consuming energy, and our source is providing it. And the source is providing this power along a single set of wires that go from a single breaker out of many breakers that are going to be in the circuit panel in this home. So, power. Well, obviously, the source needs to provide enough power to drive all these devices, and they might not be on all the time. But if I total them all up, that's where 2,156 comes from. So here's the 2000s, and then 23 and 13 is 36, and then plus 120 is going to give me 156. Now, let's see what that means for the total amount of current that needs to be provided by this circuit. So I'm simply going to add all these up. And as we know in parallel circuits, the voltage is the same, but the currents add up. So I'm going to have 8.33 plus and 0.19 plus 8.33 again plus 0.11 plus 1. And that gives me 17.96. That's actually a problem. And I'll tell you more about that, but let me just finish this calculation. So R is V divided by I, so 120 divided by the number I just got gives me an effective resistance of 6.68. Okay, what's the problem here? Well, the 17.96, or about 18 amps, exceeds the 15 amp safety limit for a single set of wires coming off the power distribution panel or the circuit breaker. And that means if all these devices are on at the same time, the circuit breaker is going to switch off. The circuit breaker is actually this little device in here. It looks like a switch when you look at it when the panel is open. And that means if all these devices are on, then that circuit breaker is going to trip. And what's the cause of this? Well, it's really the big ones right here. So the coffee machine and the microwave, having these on at the same time, both at the same time, is going to exceed 15 amps just by their own presence. So really, you can see the light bulbs and the fan don't really amount to very much. So excuse me, the microwave and the coffee machine need to be on different circuits. This is part of load balancing. So you might have in your home or apartment, you might have one circuit that covers two bedrooms, but in the kitchen, which is only one room, still needs to have multiple circuits. Otherwise, we're going to see an overload because of the appliances that are present. Usually when a circuit breaker pops or disconnects or deactivates a circuit, it's one of two reasons. There's either a short, which is bad because that means the current's going in some direction that you don't know and it's quite high. Or it means that there's too much power being provided by that panel. There's too much current being drawn and it switches off because of that. Okay, let's go ahead and build this circuit. So I've already done a little bit of pre-work in this, and I have changed from like the what you see is what you get mode to more of a schematic. And so here's my source, and I changed the value to 120 volts. And here's a fuse, and you can find fuses by just scrolling down. There it is. And I checked by double clicking it. I'm going to change the rating from 7.3. I'm going to move it up to 15 amps. There we go. Get close. Okay, good. And this is saying what the effective resistance of the fuse is, 4 milliohms, which is really nothing. And that makes sense because you can see our fuse is in series with our circuit. And that means it should have a very low resistance, so it can pass all the current without using any of it. So I'm going to now represent our load. I'm going to bring this in and I'm going to rearrange this. So this could be my coffee maker or something like that. And I want to use those values that I've come up with. So if I double click on this, then I can change the resistance to what I need. I'm just going to hop back here and we'll build these one by one. My coffee machine should have a resistance of 14.4. Okay, so we're going to change this to be 14.4. It looks like I can't go that low. Um, let's do a couple of the ones that are bigger and then I'll find a different symbol. So 1091 and 632. So I think I can do those. And 120, I think I can do those. Okay, so let's do 120. There we go. Good. So that's going to be one of my devices. And I'm going to take a look at the other ones. Where's another resistance I can do? This one, 1091. Sounds good. Can do that. And so I'm just going to right click on this. Whoops. Can I not? Control C, Control V. Oh, doesn't work. Okay, so I just need to grab another one. And if I put my mouse over here, I can rotate it and try and line it up because I need space for 5 of these altogether. Good. Okay, so that's looking all right. Let's get ready to type in the value. I'm going to pop over here and just remind myself that I'm looking for 1091. And I think 1090 ought to be fine. Okay, good. That's another one. I'm still trying to get the space to work. I think I have another big one that I can use. That's the other light bulb. So I'm going to just swing this around so it's vertical. Place it right next to it. So again, these LEDs have very high resistance because they don't use a lot of current, but they provide really bright light. So 632 is the other one I can do. And then I'm going to have two 14.4s. So 632. 630 is going to be enough, I think. Whoops, a little too far. There we go, that's 630. I have two more devices to do, but I'll just do those as light bulbs because they are light bulbs, right? Now this is a little hard to rotate, so I'm not going to bother with that. But these are both the same because they're 1,000 watt devices. So 14.4 is what I'm looking for. So they're not light bulbs; they're actually microwave and the coffee maker. So 14.4. There we go. 14.4. Good. And got one more, and I'm going to make that 14.4. And so thanks for sticking with me. It's like watching a cooking show, I guess. 14.3 is what I'm looking for. All right, close enough. Good. All right. Now it's time to connect them. Now, one of the instructions says make sure you put a switch in for each one. So, and make sure it's open because we're going to start off with nothing being powered initially. Great. Where are we going to find switches? They're over here. And so again, I'm going to bring in a switch. I'm going to connect this, and this is open, and you can see the effective resistance of an open switch is infinite to infinity and beyond. And we're going to keep on building those switches. It doesn't really matter if they're in front or behind the resistive device. That doesn't really matter. Ooh, okay. One more switch. There we go. Good. All right, and then I have a bunch of wires up here that I can use to start making connections. So I'm going to pause the recording while I build this. Let me just finish off one. So I need to do these one at a time because each one needs a connection. So we'll bring this wire in here and then bring another wire in. And once the two circles connect, then you can see it goes from red to black. I need to come down here. I can't just string one wire across because each of the wires only has two connections. So I can't really do multiple connections. So I have to build them step by step. And here comes the next one. And I'm trying to do this with right angles so it's easy to see what I'm doing. Oh, nope. I don't want to do that. So I'm just going to cut that. There we go. And then connect that. And I'm just trying to use multiple wires so it's really easy to read. Okay, good. Can always move these around a little bit to clean it up. All right, I'm going to pause my recording right now so I can finish this up and then we can come and talk about it. So I'll be back in a second. Okay, I'm back and the cookies are done. You can see that my circuit is complete. And here we go. So I'm going to gradually turn these on. And so I can do that by just clicking on the switch, right? So now we have current flowing. This is the ceiling fan, I believe. And so we're drawing current. And remember, our circuit breaker is set to conduct as long as the current is less than 15 amps. And then I'm going to turn on some of our other appliances. So this is a light bulb, um, an LED light bulb. So that's on. You can see the arrows are moving very slow because it doesn't draw very much current. Here's the brighter light bulb. So I turn that on and I can see that the arrows are still moving slow, but they're faster than this other one that had higher resistance. So the LEDs produce quite a bit of light with very little current because they're extremely efficient. I love LEDs. I could talk to you about them for a long time. But then let's come to the other big use. So we have a coffee maker and we have a um, a microwave. So I'm going to microwave. I'm going to warm up some shrimp and grits leftovers from last night. So, oh yeah, so that's very hungry. The microwave loves its arrows, so it's sucking them right down. And then if I go to turn on the coffee maker at the same time, so this could be like a Keurig. It only operates for a minute, but if these two happen to be on at the same time, let's see what happens. Oh, okay, and everything shuts down. So, and we don't get all the lights go off because the circuit breaker is controlling the current through this entire circuit. So let's see if we can turn this back on. I don't know. Looks like it's broken. Now it's back. Yeah, there we go. Okay, now I reset the circuit breaker and now the lights are back on. So I should actually unplug one of these two devices and plug it into an outlet that's further away, which is probably going to be on a different circuit. And there are, of course, devices to help you out with this. All right, let's go back and take a look at this assignment. So now at this point, it says gradually close all the switches in the simulation and then answer the questions that are going to be below. Whoops, I did this wrong. Oh, all right. I should have left this blank. So in the copy you're going to get, I'm going to have my example, and then I'm going to have some questions for you down here too. Anyway, that's the end of this video, and I hope it helps you complete this assignment. If you have any questions, please email me, text me, send smoke signals, anything that communicates. All right. Have a great day, and thanks for watching.